Today I want to talk a little bit about causality in epidemiology. Generally, we assume things are causal, but there's a tendency to not validate our beliefs or our assumptions. Here's some examples of beliefs that we have. During the COVID-19 pandemic, there was talk that vitamin D reduces the risk of COVID-19. So that's a belief, not necessarily, it is a hypothesis, but it's also a belief because many people act upon it without testing the hypothesis. Another one is that zinc reduces the likelihood of common cold symptoms. I use zinc regularly, so I've fallen for that myself. Another is that, and this one has been shown to be a cause, but it still is started as an observation: cigarette smoking causes cancer. So these are all assumptions that are easily testable. And actually there are data now that contradict the first two, so these contradictions make it difficult to say there is causation. So let's talk about what we need to do, or what conditions must occur or must be present in order to conclude causation. So the first is a temporal relation between variables, right? Between the cause, the putative, not known but assumed cause, and the effect. For instance, with cigarette smoking and lung cancer, we do have a temporal relation. Exposure precedes disease. It's very rare that somebody with lung cancer would start smoking. So it would be hard to conclude that lung cancer causes smoking, but cigarette smoking precedes lung cancer. So it is possible then that it's a cause. So notice that you need all of these, or many of these, or most of these in order to conclude causation. One is not enough. Strength of the association. The stronger the association, the more likely there is a causal relation. When I talk about association, one way to measure association is through a correlation analysis. Another way is something we'll be doing in class, a chi-square analysis. So depression and self-esteem are highly correlated. They're like in the range of around 0.6 to 0.7 on a correlation scale. So they're pretty strong, although they're inversely related. Like higher depression results in lower self-esteem and vice versa. A dose, so now we're basically accumulating evidence to try to conclude that something is a relation is causal. A dose-response relation, so an increase in the dose results in an increase in the likelihood of the health outcome. A really easy example is alcohol and intoxication. If one says, does alcohol cause one to get intoxicated? Well, yeah, the more you drink, so this is a dose-response relation, the more you drink, the more intoxicated one is. Replication of research findings, this is the one that's least likely to occur because of laziness or a publication bias. Researchers do love doing research, but journal editors don't like publishing all research. They prefer novel findings, but we need replication of findings in order to determine causation. I know it's not that interesting to read the same thing done over and over again with different samples, and it must be done over different samples from a population, but that's what we really need. We need replication of research findings. Biologic plausibility, so is the relation that is being studied biologically plausible? So is there a biological explanation? Can we identify a biological explanation? Here's an example. Is there a biologically plausible reason for stress causing heart attack or heart disease? Yeah, stress is related to the release of cortisol, and cortisol is related to blood pressure. So and that's a risk factor for heart disease. So it's biologically plausible that stress could cause heart disease. I'm not saying that it does, but it's plausible because of these mechanisms. Cessation of exposure. So we talked about dose-response relation. Well, this is related to that, right? Cessation of exposure is what happens when we take away the exposure. So if you eliminate the exposure, it should reduce the likelihood. By the way, likelihood is the same as probability. Those two words are interchangeable. Of the health outcome, one example would be quitting smoking decreases the likelihood of lung cancer. That's something that's been studied greatly. Another more common one that you would see in your own personal life is removing an allergen reduces the elimination or eliminates some allergic response. So if you're allergic to pets, removing the pet, I mean, you can test this. This is when you can test very directly. If you remove the exposure, you should eliminate the outcome of interest. Consistency with other knowledge. So this is what we call coherence. Data are consistent with our expectations. Here's an example. The relation between depression and suicide is consistent with our expectation that depressed individuals are likely to contemplate suicide and have higher levels of suicidal ideations. Specificity of association. I consider this a debatable criterion. So according to this criterion, a risk factor is associated with only one health outcome and no other, because there's so often risk factors are associated with more than one health outcome. For instance, many non-infectious diseases have multiple causes. For instance, cigarette smoking doesn't just cause lung cancer, it can also cause emphysema. But it's still a cause, right? So it's not, there's not just one outcome associated with it. Lung cancer itself has multiple causes. It could be smoking, could be air pollution. One of my favorite examples are concussions, because there was this belief that, especially with football, that all the hits that one takes, all the concussions one has, makes one very unstable. And often when we have these high-profile athletes committing suicide, the belief is that, well, it was because of football, it was because of the concussions, but concussions are also associated with other outcomes like CTE, chronic traumatic encephalopathy, as well as mild cognitive impairment. So they're not just related to suicide. So there's no, those are just, that's a leap, and what we call an intellectual leap of faith to make that proclamation, right? Another example is COVID-19. So there's this belief that it causes myocarditis. So there was this really big concern, especially for younger people and athletes, that if you get COVID playing sport, you can get myocarditis and you can die, right? But other viruses cause it, including the seasonal flu, right? That can also cause myocarditis. So it's not a happy thing, but that's not the only potential causal factor. So the idea here is that when you before you can conclude causation, one has to go through a great deal of reasoning to determine whether or not, based on data, we actually have causation, and that's something that's missing, especially when it comes to more recent issues we see in the media, like believing that, for instance, a horse dewormer will cure or prevent COVID-19. I mean, there isn't enough evidence. There isn't any evidence, as far as I know, that occurring. I don't even know where that started from, but there's a tendency for a lot of people to jump to these conclusions without looking for the evidence. So let's look at whether or not all causal factors result in a disease outcome. There are two types. We at least have two types of causal factors. One type is necessary and the other is sufficient. So necessary causal factors and sufficient causal factors. If an exposure is required for the outcome to occur, the causative factor is necessary. Like HIV is necessary for AIDS to occur. So it's necessary. If a health-related state or event always occurs because of exposure, the causative factor is sufficient. So, for instance, tainted chickens or tainted turkey, God willing, nobody ate tainted turkey, served at a potluck is sufficient to result in gastroenteritis, but is it necessary? The answer is no. There are other factors that can lead to it as well. Other foods, one can be, as you know from your exam, we talked about primary and secondary transmission. It can be transmitted, the pathogen can be transmitted indirectly as well, through a surface or touching somebody's, shaking somebody's hand who has the infection and then touching your mouth. So it's while the turkey, tainted turkey or tainted chicken is sufficient, it's not necessary. Now, we talked about this before, but it's worth repeating since we're dealing with it here. And a couple of things we've discussed before, different types of causal relations. We have direct and indirect causal relations. When there's a direct causal association, also known as a direct effect, we have no mediating mechanisms or no intermediate factors. So here's an example. So again, and eliminating exposure will eliminate the adverse health outcome. But here's an example. So trauma to one's skin, like somebody hits you, results in a bruise or bleeding. So that's a direct causal association or direct association. Well, salmonella results in enteritis. Right, so those are direct. There's nothing intermediate. Sometimes the associations are channeled through some mediating mechanism. And actually, a moment ago when I was talking about suicide and concussions, CTE or chronic traumatic encephalopathy is an example of a mediating mechanism, or potential mediating mechanism. So it's possible that concussion leads to CTE, which may lead to an increased likelihood of some erratic behavior. So we could think of that as a mediating mechanism. Isn't another example, exposure to smoking, whether it's vaping or cigarette smoking, influences one's beliefs about the risk. Like, for instance, if one sees a lot of people smoking around them, the belief may be that smoking is not dangerous, so that there's little risk associated with it, and that could cause one to initiate experimentation. So that's an example of a mediating mechanism. Or here's another example. Poor diet and stress may cause high blood pressure, which in turn causes heart disease. So a lot of things in our world are very complicated in the way they are related. There are mediating mechanisms involved. One should always conceptualize potential mediators or moderators, although moderation isn't something I'm discussing right at the second here, but that's something else to consider, like whether the effect of exposure on smoking differs for males and females, or for some other possible factor. In terms of generating hypotheses, we discussed this early on when we were talking about how observation plays a big role in epidemiology, and I had discussed inductive reasoning, but this is just a good time to review it and make sure you're familiar with it, familiar with the difference between inductive and deductive reasoning. So inductive reasoning is going from specific to general, and the examples given in your textbook or ones that I discussed are really nice examples of inductive reasoning. So, for instance, seeing individuals not washing their hands, or seeing medical students going from autopsies to a clinic where women were giving birth and doctors not washing their hands led Ignace Semmelweis to hypothesize that the cause of childbed fever was the transmission of some pathogen via the hands. So that's an example. Deductive reasoning is going from general to specific. Most of what you read in the literature is based on deductive reasoning. Individuals start with theory that they like and use that theory to determine or to generate these interesting causal hypotheses. I'm sure you do it all the time. I hope you do it. I hope you do it. You read something interesting and then want to make a nice hypothesis out of it. Let's talk a little bit about statistical inference. And when we make inferences, we're basically testing our hypotheses statistically. So this is kind of a review, hopefully, for you from stats, because stats is a prerequisite here, or maybe at worst you're taking it simultaneously. And if you are, I know a couple of people who are taking our course simultaneous with a stats course. And if you are, you already covered this, so hopefully this is just good review for you. So there are two different types of hypotheses. The one that we're interested in is known as the alternative hypothesis or the research hypothesis. The one that we're interested in rejecting or negating is known as the null hypothesis. Why it's called null, there are many different reasons. Perhaps it's the one that we want to nullify, or generally when we're comparing two groups, we'd say the difference is 0, which is also null. In research, we don't specify the null, but it's always inferred. The interesting thing about causal inference is that we start with the hypothesis that we're wrong. Right, so if I'm testing my famous sunshine pills to see if they improve one's happiness, I could compare them to a placebo. My null hypothesis would be there's no difference between sunshine pills and the placebo in happiness. My alternative is that people who take sunshine pills will be happier than people who take the placebo. But I have to start with the assumption that my pill does not work. It's just like when we're dealing with issues, whether it's vaccination or masks, the vaccine producers have to start with the assumption that the vaccine does not work in preventing something like COVID. You also have to start with the assumption that masks do not work when you test them out. Now, here's the problem, is that a lot of individuals who are not familiar with this, with scientific reasoning, will assume that they're right regardless of well, actually, they'll just assume they're right. And they'll place the burden on the consumer to prove them wrong. As a scientist, we place the burden on ourselves to prove that we are right. So we start with the assumption that we are wrong. These other people start with the assumption that they are right. So for instance, when I was listening to somebody on a radio podcast, and I was waiting for him to talk about something I wanted to hear about, and instead he started spewing nonsense about mask wearing. He said, there's tons of evidence that masks do not work. I'm thinking, oh really? Where? Can you find it for me? Can you show it to me? The assumption that person made was that masks do not work. And he should have started by assuming that they do work, since he wanted to prove that they didn't work, right? Whereas I like to prove that they do work, so I have to start with the assumption that they don't work. But you always have to have the alternative. You have to have the null and the alternative hypothesis, and you're always starting with the null. We generally don't specify this. If you read a paper, you're not going to see null and alternative hypothesis. You'll just see the research hypothesis. By the way, the symbols for null are H sub 0 and alternative, either it's H sub A or sometimes it's H sub 1. And then once you get your results, you have to interpret your results. So I'm not going to go into great detail on how we do that, because that would actually have to involve us doing a statistical test, although we will be doing some. Actually, in this chapter, we're going to deal with the chi-square test. So we will do that, but generally there's some kind of a probability value associated with a test statistic result. And there's some threshold for what we consider statistical significance, right? Without going into too much detail, that's how we determine whether or not we can reject our null hypothesis. Just because we reject our null hypothesis doesn't mean that we are right, but it's some evidence in our favor. In order to be considered right, we'd have to pass all those causal those requirements for causation that I just discussed, right? Especially replication of findings. But people do make errors, and that's normal. People make errors when making inferences. There are two types of errors that one can make. We call them the type 1 and the type 2 error. So type 1 error, I know you're familiar with this. You may not remember what it is, but you're probably familiar with an alpha. And you're probably very familiar with alpha equal to 0.05. That's an alpha that's used in most statistical testing for some reason. It's the most popular one. Alpha is the probability of a false positive result. Right? A false positive result is when we reject the null hypothesis when we shouldn't have rejected it. Right? So now, forget a moment about how we use it statistically, and just let's talk about a false positive result. This is not uncommon. One of the reasons why it occurs is that individuals do too many analyses with a set of data. Like, for instance, if you have 3 levels of a drug, high, moderate, and low, high, moderate, and then placebo, sugar pill, you can make multiple comparisons. You can compare high to placebo, low to placebo, and high to low dose. The more comparisons you make, the more likely you are to have a false positive result. Whatever the alpha is that you choose, and this is a personal choice, and hopefully when you took stats you learned about that. But say if your alpha is 0.05, every comparison you make cuts into that 5% probability of a false positive result. And you actually start increasing your probability. That's something and this isn't as important for this course, but that's something we call family-wise error rate. If you're taking stats with me, you know we calculate it. We know how to calculate that. The opposite, by the way, the opposite of a type 1 error is confidence. And there's too much. It's too much to go into why it is, or I should say not the opposite. The complement of it is confidence. So 1 minus alpha is confidence. And when we were doing our confidence intervals, we did a 95% confidence interval. That's associated with an alpha of 0.05 because 1 minus 0.05 is 0.95, right? So, but if you're interested in that, we could always discuss that. I'm sure most people aren't, but we can, if you want, you can ask me. Another type of error is the type 2 error. We call this beta, or as some British people call it beta. I like that. Beta is failing to reject a false null hypothesis. This is a really bad problem if somebody paid you to do research. So here your null hypothesis is wrong and should be rejected, but for some reason you can't reject it. That really stinks. I mean, talk about a way to not keep a job, right? This is your inability to do your job. Reasons for actually, I never mentioned a reason for, besides multiple testing, a reason why one might have a type 1 error. If you have a high alpha, so alpha is this probability of a false positive result. And I said it's generally 0.05. So researchers actually set what they accept as the probability of error. So, like, for instance, a researcher generally accepts that a 5% error or less is acceptable. Like, I could make a mistake 5 out of 100 times, but that's okay because I'm making a correct conclusion 95% of the time. But researchers set the alpha. If you set your alpha higher, you're more likely to get a false positive result. So sometimes you'll just get a statistically significant result because of how high your alpha is. Even though if you decrease your alpha, it wouldn't have been significant. So type 2 error is failing to reject a false null hypothesis. This occurs mainly when individuals have sample sizes that are too small. In statistics, there's something known as power, and power is the ability to reject a false null hypothesis. So as you can see from this little equation here, power is the complement of a type 2 error. So 1 minus beta is equal to power. So the higher your power, the lower your probability of a type 2 error, right? So you want to have a lot of power. Power is determined primarily by sample size. You can also increase power by increasing your alpha, going from 0.05 to 0.10. That'll also give you more power. However, if one wants to be very conservative and set their alpha very low, like at 0.01, like a 1% chance of a type 1 error, then you'll increase your type 2 error. You're likely to fail to reject bad null hypotheses. So that's just something interesting, and I need you to know all this stuff, right? So study up on it, and when we're in class, we'll do an analysis called the chi-square, where we can compare categorical variables like nominal variables and ordinal variables. That's it. Thank you very much.